Okay, so this is the introductory lecture to the Advanced Security and Network Forensics module. The key objectives of this lecture are to provide an outline of risk and some of the terminology that's used, to give an outline of some of the range of threats that we are currently under, to have a basic overview of client-server connections. So a key focus of this module is the use of services, which are becoming a key element of an internet or web-based infrastructure. So for this, we'll look at the common services that are provided with inside Windows and Linux, and then look at service-orientated infrastructures. And at the end, we'll provide a practical background into Windows and Linux for services logging and auditing. So the module itself has an associated VM image. So we have a Windows image and a Linux one. So we'll do some practical tutorials at the end of this presentation for these two. Okay, so let's start on risk analysis. So risk is an important element when we look at security, because we've got to see if it's worth it or not to mitigate a certain threat that we are under. So we always take a certain element of risk. So with this, we would typically take the likelihood of the risk of a certain threat, and then evaluate its cost. So in this case, in this region, we have a risk which is highly likely, and it has an associated low cost to mitigate against it. So probably in this region, then we would hopefully mitigate against a certain threat. When we're in the top region here, we have a low likelihood threat, and it has an associated high cost. So it's unlikely that we would mitigate against certain threats in this region. In the other two regions, then the choice is less clear. So in this region here, we have low likelihood and a low cost. So we would make a decision as to whether we want to take a risk or not. And up here, we have a high likelihood and a high cost. So we've got to again wonder if we should take the risk. So it's in these two regions that we must use our judgment in whether to mitigate against a certain threat. So obviously one of the major costs that we have is the cost to repair the damage after a threat has occurred, after an incident has occurred. So in this case, we might define the likelihood of the event. We would then look at the annual loss expectancy. How much is it every year we're likely to lose if we have to repair some damage. And then we would define what the cost is, and then take the likelihood and come up with an overall total annualized loss. With each element of a computer system, obviously the probability that an event will happen varies for the type of event it is. So in this case, we can see that programming input errors are highly likely, but we go right down the scale to an external power failure, which is much less likely to happen. So there are generally probabilities associated with each of the risks that we can have. So we can see in this case for a password compromise, system entry is more likely to occur than an uncleared visit. Same for fire, a minor fire is fairly probable, whereas an explosion is highly unlikely. So let's look at risk management. The major problem with risk and threats is that often different types of employees will use different language to describe risk, and it's a major problem in that we have often a technical context where we can describe risk and technical threats in one way, but that can be different to the way that more business focused people can talk. In fact, Wulch described that get 2 risk management experts in a room, 1 financial and 1 IT, and they will not be able to discuss risk. So it's important that we lay down the basic vocabulary that we should use, define the definitions, processes, metrics and standards. So CORAS, which was a research project in the EU, defined a basic ontology for a threat. So in this case, a threat may reduce the value of an asset in a target of interest in a context. Again, we might say a threat may exploit a vulnerability which opens for a risk which contains an unwanted incident of a certain likelihood. So in this way we can define the basic language that we use to define risk. Over here we can see a security policy protects an asset in a target of interest in a certain context. CORAS also defined risk management methodology. With this we have consultation, communication throughout the process, and there is a monitor and review cycle that goes on at the same time. So for risk management, we identify the context that we're going to work within. We identify the risk. We obviously consult and monitor. We then analyze the risks. What is the frequency of it? What are the consequences? And then for this we can define what the level of risk is. So with this we can go back to our probabilities of these risks occurring. Then we can evaluate them in some way, and at the end we can say whether we accept the risk or we don't. If we don't accept the risk, then we must treat it in some way and define a mitigation strategy. So along with defining an ontology to be able to get the basic definitions correct, we also need to define a taxonomy which will classify our subject and define the relationships between certain entities. So let's look at a security incident taxonomy that was developed. So in this case, a threat is achieved by attack tools for vulnerabilities with access, which results in certain objectives. So in this case we might classify a threat here, a hacker, spy, terrorist, and so on. And then the attack tools might be user command, script, autonomous agents, toolkits, distributed tools, data taps, and so on. And then these attack tools are used for certain vulnerabilities. So it might be an implementation vulnerability, a design one, or a configuration one. And then with access, might be access to files, processes, objects, invocations, and so on. And then the results could be related to the corruption of data, the disclosure of information, a theft of service, or even a denial of service. And then for the objectives, we might have challenge status, political gain, financial gain, damage, and destruction of an enemy, and so on. So let's look at some practical threats to see the range of the threats that we're under. So two well-known threats that have been around for a long time include eavesdropping. So eavesdropping involves actually listening to a conversation or intercepting the communications. So with this, we need to make sure that our staff are well trained so that they do not pass information to others who might be listening. We also need to make sure that we have secure communications when we need it, to make sure that anyone with a tap on the line cannot actually listen to any of the communications. Logical scavenging is a major worry, especially as we're moving towards large-scale storage, and it's one of the top risks, and it typically involves scavenging through discarded media for data. Andy Jones and Professor Andrew Blythe from the University of Glamorgan analysed 300 disks recently and found that 34% of them actually still had personal information on them. So it's important that companies have policies on how to get rid of old computers and media which is not used anymore. Interference is another problem that we can have, especially if we have something like a wireless network. If we use communications which are based around wireless, then a malicious party might intentionally cause noise into the system which might reduce the quality of service on our wireless network. Along with this, we might have physical removal of the equipment and even damage of it. So it is very difficult to get any security into the system if someone actually removes the devices which are providing the security elements. We can also have visual spying. Visual spying involves actually someone watching a user for their keystrokes and their mouse clicks and so on. It's very difficult to guess a password just by watching keystrokes for the first time, but an intruder might watch keystrokes over a length of time and determine a password. We can also have misrepresentation. With misrepresentation, then we actually have a process of deception of the user, and it typically happens over a telephone where someone might phone a user and say that they are actually someone else, such as a system administrator asking for a user name and password. With this type of problem, often we make sure that our users are well trained and actually never give away the details. Trojan horses are a major threat for us. With a Trojan horse, we have the threat within inside some other vehicle, delivery vehicle. In this case, we have a Trojan virus with inside an email. So once the email is opened, then the Trojan might be installed and then could go off at some time in the future, which leaves us to logic bombs. With logic bombs, we have typically a dormant piece of software which will monitor and wait for a certain event to happen. So it could be triggered by the date, time, a certain user logging in, or it could be triggered from I control from outside. So logic bombs are a considerable threat to us. Then we can have malevolent worms. In this case, it is a piece of software which mutates itself and will typically reduce the quality of service on the network or on a certain device as it mutates itself. So we can see here in this case it might hog the CPU or memory, network access, or even accesses to the disk, and this generally reduces the quality service on the machine or the network. Viruses are a problem, and viruses tend to self-replicate themselves and will generally move from host to host. A particular problem at the current time is denial of service. With denial of service we have Eve here, and Eve might make continual requests to a web server, and unfortunately Bob gets a lower quality service because he tries to access it, but doesn't get the same quality service as he would, as Eve has reduced this. This is often mitigated against by setting up firewall rules which will block Eve's access to the site. But with distributed denial service, Eve has managed to distribute herself around the network, so it's very difficult to implement this type of defense. Along with this, it's very difficult to define the difference between a malicious access and a non-malicious one. So Bob here has a non-malicious access to the website, whereas we can see Eve with the red markers has done a malicious one, and it's very difficult to see for the server to tell the difference between the two. So we either have end source denial of service, where it is the end target which has its resources reduced, or it could be through network exhaustion, where the general network infrastructure is saturated so that network accesses struggle to get through. The mitigation strategies here we'll look at in the second unit. We might also get an active attack, and that normally involves inserting incorrect data to cause some problem which causes the system to act as it was not intended. So in this case we get what's called a buffer overflow, where the user has inputted a long string of data which causes the memory to leak into other areas. See again here the user ID has been made too long, which might exploit a certain vulnerability in the system. We'll look at this in more detail in Unit 2. Another threat that we have is inference, and again we'll look at this in more detail in the next unit. So with this, there are certain queries which are not allowed on a database. So in this case we might bar the actual access to individual marks for users, but we allow the averages to be taken from more than one user. So in this case the intruder could actually determine the average marks by running 3 queries, finding the average mark of Bob and Alice, average mark of Bob and Eve, and the average mark of Alice. We do some calculations and we can actually calculate each of the marks by inferring it from the averages that we get. So we'll have a look at this in more detail in the next unit. Covert channels are a way that someone can actually add information and data into elements of the data communications which aren't actually used for the communication track. So in this case, Bob has inserted the letter G within the TTL field of the IP packet and the letter O. So if Bob and Alice know where to look, then we can see the word go has been inserted in here. Anyone looking at the message itself would see hello and goodbye, but there is a covert message hidden within inside these data packets. So later on in the module we'll look at timing channels where Bob and Alice can agree to set up things at certain times, and also for a storage channel such as where we modify an object as we have done in this case. Spoofing is a particular problem at the current time. So spoofing is where a certain user pretends to be something else, or a certain device pretends to be a valid device. So in this case it might involve a wireless access point, and we connect into the wireless access point and we think it's a valid one, where someone comes along and spoofs that device and we connect to a malicious one. Along with this we can have impersonation, where users pretend to be other users. Piggyback attacks involve piggybacking a message onto a valid message. So in this case Eve has added the word goodbye onto the message hello. And network weaving is also a major problem, and in this way the source of an intrusion can be hidden through the weaving of activities, so it's very difficult to actually find out where the original source actually came from. Authorization attacks typically occur at a low level of access, and then will move up the levels to gain a higher level of access each time. Trapdoor impersonation, it involves where valid looking web pages such as this can be set up so that the user thinks they're actually accessing valid content, but as we can see in this case the page is actually malicious. In this way we have a trapdoor where the user feeds in some details that could be used for malicious purposes. Okay, so another key objective of the module is to look at services, and especially services within a service-oriented architecture. So services have generally grown out of having local DLLs. So we can have local DLLs, and our program access these to be able to get access to certain pieces of code. So then we moved from having DLLs to having local services. So with a local service we can run a program, and then the host itself can access its own services. So those services could be print services, it could be file management services, web services, and so on. Within inside the local machine there is typically a local firewall, so the firewall itself might block certain access to even these local services if they are deemed as malicious. What we've got to watch is that a malicious program installs itself and runs as a service on the machine. But more and more the services are being moved away from our local machine onto the network. This allows our machines to be fairly lightweight in that more and more all we really need is an access to our services and then some sort of binder to be able to bring these services together. So we can have our services contained within our demilitarized zone to provide our domain services. So this might be a proxy server, direct-to-server, web, FTP, email, and file servers. And with this we might have a local firewall which might block access or not. Then we can have remote services, so if our organisation doesn't have all the services that it needs, then it might use some external services. In this case we might have an external email server, web server, and so on. And again we can have another firewall in the way which could block the accesses or not. So for example, a typical service which is blocked is SMTP, which is an email relay. So it's very unlikely that we can actually get through a firewall on the SMTP port, because it's seen as if we could be sending spam email. And more we're moving also towards getting the services within the cloud. So in this case we have directory services, email, web services in our cloud architecture. So with this we can have static pointers to all these services. It tells us what IP address, what port it's on. With cloud services we don't actually know where they are, and at any given time we will be told that we can then access the service, which might be real or not. We get a pointer to it and the service exists at any given time when we access it. The basic concept that we have is that we have a local IP address for client-server communications, we have a local IP address, and we have a remote IP address. So these addresses allow us to get over the network to be able to deliver from one host to another. To be able to connect and get our data transmitted, we use the TCP protocol typically. And TCP involves setting up a TCP port, and it's typically a well-known port on the server. So a well-known port for a web server is port 80. And then we set up a host port which is unique inside our own machine. Just to take away some of these scribbles. So we set up a unique port locally, which isn't being used. Okay, so let's say that we set up port 1026. So the binding between this IP address and this port with this IP address and this port will be unique over the whole of the internet at that given time. So no other connection on the internet can have these four details the same. If we connect to the same web server again with a different connection, we'll use a new TCP port. In this case we might use port 1027 and connect to it. Again, this will be unique over the whole of the internet. Once this connection is gone, then we can reuse this source port again. But we can see over here that the well-known service typically uses a well-known port that we can access. On our side, we will use our own source port to be able to identify the communications. Okay, so we can see this basic principle here. So we have our IP address of our service and our host, which really gives us the location of it for the delivery and the transmission of the data packets. We then have a binding between two ports. So our data really goes between one port and another. It gives us a logical binding for our data. And then we have our client, which accesses a certain service. And it's these two parameters here on the client and these two parameters there on the server, which gives us our binding between the client and the server. So most communications that we have on the internet are based around this client-server architecture. For the next generation of communications is likely to involve a web infrastructure, and we'll look at this in more detail in the later part of the module. And with this, users are typically mobile and can be logging in from many places around the network and not necessarily inside the organizational network. So more and more we're differentiating identity from rights. So in this case, a user might identify themselves to an identity provider. So in this case, the user provides their user credentials. It might be a username and password, or it could be a biometric method, such as a fingerprint. And then the user gets a ticket back, which can be used to consume the services. This can be a federated identity management. So in this case, our organization might trust Windows Live as a login, or Google, or VeriSign. So there can be a number of identity providers set up that provide a trust level. So in the UK we have the Athens infrastructure, where anyone who is registered with inside the academic domain can log in through Athens, which is a trusted identity provider. Then with the ticket, we can then go to the service provisioning module, and we provide that ticket. The ticket is then checked for what it is we want, and how long the ticket is valid for, and the identity, and so on. And it also looks at the rights of the user to access the service. Once it has been agreed that they can access it, then the service might be created inside a service infrastructure, such as creating a web service. It could be virtualized, or it could be a real resource, or it might be to some storage. It could be the user's storage. Once it's invoked or created, then a pointer is sent back to the user, which will define where the service actually is, which port it is on, and so on, and then the user can actually consume it. So there'll be a time limit for the consumption, and then that service might not exist anymore. So we can see this is a much more dynamic infrastructure, that we can use different identity providers to provide their identity. We can have tickets that are valid for a certain amount of time, and then we can take rights away from users as required. So this gives us our next generation infrastructure, and we'll be looking at this in more detail inside the module. Another area that we'll look at inside the module is the area of cloud computing. So cloud computing gives us access to resources on a pay for usage basis, but from a security point of view, it gives us many issues that need to be addressed. So basically there's several layers of this infrastructure. We can have hardware as a service. So in this way we can actually buy hardware resources as we need them. So we might have a local machine, but then we could purchase another machine that would act as a backup for our own machine. more and more we can have infrastructure as a service, which would include hardware as a service also. And in this way we can get access to storage online. We can have computing power that we might not be able to get access to. So if we had a PDA device and it didn't have the capabilities of doing powerful encryption, then the device could use a specialized computer inside the infrastructure to be able to perform the complex operations. Then above this we can have platform as a service. This is where we start to see our services appear inside our service-oriented architecture, and we can use sophisticated web services to provide a range of tasks. More and more we're moving towards using web services to provide a whole range of support for software, as port 80 is often the port that is allowed through a firewall. And then at the very top we can actually even provide all our software as a service. So at the lowest layer we can have servers which come online as we require. So an example of this is the Amazon Web Services, where we can get storage and we can get machines which we can create online, and then we get access to them through some sort of API or from a command line interface. So the typical model used for this is a pay per usage. Then at the level above that we can have a platform as a service. So examples of this include the Microsoft Azure, Google Application Engine and the Amazon EC2, where we get services provided for us that we can then consume. So it might be a data storage service, maybe a user interface creation service, and so on. The typical protocols used to find these services and to find out how they operate and how to interface to them are SOAP and WSDL. These protocols allow us to interrogate the service to find out what it does and what the formats are of the data transfer. And SOAP allows us to seamlessly go between services on different types of operating systems. And then at the very top we can have software as a service. In this case we can get access to a whole application program over the internet, such as Twitter, Office, email packages, and so on. Another key focus in the module is to look at virtualization, which is one of the major growing areas at the current time. So with this we now have hardware which is powerful enough to be able to run multiple operating systems at the same time. And the market leader in this is VMware. So with VMware we can either use a virtualized environment which is installed on top of our base operating system, such as with VMware Workstation, and then we can run our operating systems on the top of it. So on the local machine we can have a localized environment where we can run Windows and other operating systems, and then we use network address translation to be able to map this virtual environment so that it can be accessed, or it can access the outside world. So this is typically a private address space here, which will link to an outside network connection so that we can get connected to the outside world. We can also use remote virtualized images. So in this case we might have a server cluster. So we have several machines, and then it's up to the cluster management to decide which machine is running which virtual environment. So in this case, one machine can go down within the cluster, and we should still be able to get access to it. So in this case, we can install it on the base operating system as we have, and then we can provide operating systems or services as required. So these operating systems could be permanent, or we can actually invoke them as required. So in the architecture we've seen earlier, we could require a service at a given time. It's then created. We can access the service, consume it, get a result back, and then the service itself could be actually deleted. So it could be a virtualized or a temporal service or operating system. Our operating system or service exists for a short time. We consume it and then it disappears, or it could be permanent, so it's running all the time, and it can obviously remember things from past accesses. Increasingly though, what we have is the VMware ESX, which is a bare metal virtualization, and we don't have the overhead of the core operating system itself, and it interfaces directly into the architecture of the machine. And in this way we can get multiple images to run at the same time along with our services. So later in the module we'll look in more detail at virtualization. Another area that we'll look at is inside role-based security, which is hopefully a more scalable way of defining rights inside a global infrastructure. So with this, we might have a domain, and we have roles inside each domains, and rather than defining for a certain identity, we assign our rights for a certain role. So a researcher has a certain rights based on their role, and a teacher might have other rights. We can then define inter-domain rights. We expose certain roles from one domain into another, and we can have a policy in between which defines the rights that one role has into another domain. And we might also have a role of a guest. So this is an alternative to the other typical methods which we use for access control, which is mandatory access control, where we let the operating system define the accesses to our resources, and we can also have discretionary access control. In this case, a certain entity is owned by a subject, and it's up to that subject to give rights to someone else. So we'll probably find that a mixture of these types of access control makes an optimal infrastructure, but it looks like role-based security is an extremely scalable technology, especially when we're dealing with large-scale domains and domain interaction. Okay, so that was the main overview of the key areas inside the module. So let's now look at the associated lab for this lecture. Okay, so the first lab that we'll have a look at is the Windows 2003 image. So in this case we'll look at some basic settings for Windows 2003 and see if we can discover the services that it's actually running. Okay, so we're using the VMware workstation here, and it just takes a little minute to start up. So the first thing we're going to do is we're going to discover the IP address actually on the machine. So what we see in this window is the local client, the local host, and we should see a VMware interface being set up. So it's likely to be this address here. 192.168.75.1 is our connection into the virtual image, and we should find that the VM image will connect into this subnetwork. This is a private address that we're using. Just takes a little minute to start up. Should get there. Obviously it's running a little bit slower because we're recording this presentation. And there we go. So we'll just send a Control-Alt-Delete in there. And we'll just put the password in. And we'll just report why it was shut down. Okay, so it should be nearly there. Once it started up, it should be fairly quick. So we've used Windows 2003 because it has a smaller footprint and can fit onto a DVD. Okay, so we have a look at the IP address that's been set up, and we can see it's 75.132. So we'll just ping from here to make sure that we can communicate. Should get there in a little minute. It's not quite there yet. Okay, so that's us now communicating. So this is from our host into our VM image and vice versa. Okay, so we've discovered that. So now what we can do is that we can have a look to see what's in the main web folder. So IIS is the main web server that we have inside Windows Server, and the main files are contained within the inetpub www root folder. So you can see there are a number of files in there. So the first thing we'll do is we'll have a look to see what services that we're actually running. Okay, so we have a number listening on certain IP addresses. So in this case we have echo, discard, daytime, quote of the day, FTP, SSH, telnet, SMTP, there's the HTTP and so on. So in this case we're actually listening on all the addresses. So if we see here specific addresses, then it normally means that we're only listening on certain network ports. Okay, so those are some of the addresses that we actually have. So what we'll do is we'll test one of these ports. So in this case we'll test the web port from outside. So if we just get our web browser running, and we do 192.75.132, we can see here that from outside the virtual image we can now access the actual web server on the machine. So we can do another test, and we can use telnet to access it. Telnet 192.168.75.132 on port 80. And the protocol we use is get/index. We can use get/iis start.htm, and here we see the actual file coming back from the web server. Okay, so this shows a brief introduction to the VM where Windows Lab. So if you continue through this, then it'll give you a background and understanding services inside a Windows environment.